Hello everyone, now let's look at section 4, connected particles. So in our previous chapter, section 2, you have looked at some examples of objects being pulled using a rope or a stick, and you saw that one of the forces acting on the object is tension. When two objects are connected by a taut rope or string, then the tension acts on both of them. The magnitude of the tension is the same at both of its ends. However, the directions at the two ends are different because tension acts away from the object that is attached to its end. So, if the rope is inextensible, the connected objects will move with the same speed and the same acceleration. Any external forces, such as driving or resistance forces, can be different for each object. Remember that to find the acceleration, you can consider them as a single object and not include the connecting tension forces. Two main models assumptions have been made here, and it is important that you know what specific effect each has. So, here are some tips you need to remember. Firstly, the term string is used for anything that transmits tension, but not compression forces, such as a rope, wire, cable, or chain. The term rod is used for an object that transmits tension and compression forces, such as a toolbar or plank. A rod cannot stretch or compress itself. Okay, so in our previous slide, we have made some modeling assumptions. The first one is inextensible. So what does that mean? Well, the string cannot stretch. And how it is used? Well, the magnitude of the acceleration and the velocity of each connected particles is the same. So that means we could treat them as a whole thing rather than separate things. Now, the string has been light, and what it means is that the string has a mass that is negligible and in the context of the system. And how it is used? Well, one, when treating the whole system as a single particle, the mass of the string can be ignored. And secondly, in vertical systems, the tension of the string is the same throughout. This is because lower parts do not pull on the upper parts. So, frequently in the exam, the last part of the question, they may ask you to comment on the modeling assumptions. So you should mention about those two words, inextensible and light, and you need to know what they mean. Let's move on to look at an example. Okay, so let's see if we can move the diagram up a bit. Right, so in this example, a car of mass 780 kg is pulling a trailer of mass 560 kg using a light, inextensible cable. The driving force on the car is constant and has magnitude of 1,800 Newton. The total resistance forces acting on the car and the trailer are 800 Newton and 600 Newton respectively. So let's have a look at this diagram. So let's look at the forces acting on the car. Okay, so here we have 1,800 Newton, which is the driving force. And let's use capital D for the driving force. Okay, and what else do we have? Well, there is a resistance force to the car, which is 800 Newton, and it's because it's a resistance force, that means it will act against the motion, and if the car is accelerating towards the right-hand side, then the resistance force of 800 Newton should be acting towards the left-hand side. And also, in the first part of the question, we know that the car is pulling the trailer, hence there will be a tension pulling the car backwards, which in this case pulling towards the left-hand side, and we use T to represent the tension. Now, let's look at the force acting on the trailer. So remember, the trailer will be moving in the same direction as the car with the same acceleration. So the trailer will be pulled towards the right-hand side, and because it's connected to the car by a light inexhaustible cable, that means the tension will be the same, but just in the opposite direction. So we can still use T in this case. And the trailer is moving towards the right-hand side. That means the resistance force of 600 Newton should acting towards the left-hand side. Okay, so hopefully you now understand how those forces acting on the car and the trailer. Let's move on to solve the problem. Part A, we're going to find the acceleration of the car. Okay, so you can see in both the diagrams, here we've got two unknowns. One of them is the acceleration and the other one is the tension. Well, we could, of course, write down two equations, one equation for the force acting on the car and one equation for the force acting on the trailer. And then we can solve the two equations simultaneously. Or, hopefully you have remembered something we learned from previous sections, we could consider the car and the trailer as a single particle. So that means we don't need to thinking about the tension between them. Okay, so why don't we draw a different diagram? So for part A, I'll squeeze in a diagram here. Now imagine this is for the car and the trailer together. So maybe I'll write down here the car and trailer. And we're treating them as a single particle. So let's think, what force is acting towards the right-hand side? Well, there is a driving force from the car. So that would be 1,800 Newton. What are the forces acting on the car and the trailer for this single particle? Well, we can see that there is a resistance force acting on the car and also another resistance force acting on the trailer. So we have 800 Newton acting towards the left-hand side and 600 Newton also acting towards the left-hand side. Something else you have to be careful here is because we're putting them together, so that means the total mass will now change. So the total mass will now equals to the mass of the car, which is 780, plus the mass of the trailer, which is 560. So altogether, that will give you 1,340 kilograms. Okay, so if we're looking for the acceleration, that means we have to use F equals ma. Now, the acceleration is towards the right-hand side, so that's going to be our positive direction. So then we'll have 1,800 Newton plus negative 800, which means it'll be taken away. So let's just write down as take away 800. And then also negative 600 Newton. And that would equals to the mass, which is the total mass. So the 1,340 comes by the acceleration A. So now we will get 400 equals to 1,340 A. And point to calculator, you should get your acceleration equals to 0.299 meter per second squared to 3 significant figure. Okay, let's look at part B. So, just to add up to this question, you can see if I consider the car and the trailer as one single particle, it's actually much quicker to work out the acceleration. Okay, part B. Now we had to find out the tension in the cable. Well, this tension acting on the car is also the same tension acting on the trailer. They're both the same, but which one should we use? Well, I would probably go for the trailer in this case because there are less forces acting on the trailer, so just make the equation slightly more easier. So let's consider all the forces acting on the trailer. And of course, if you use all the forces acting on the car, you should get the same answer anyway. Right, so on the trailer, we're going to consider F equals ma. And the force, well, because the trailer is going to the right-hand side and tension is going in the same direction, so tension is actually positive in this case. And the 600 Newton would be negative. And that equals to the mass of the trailer, which is 560 times by the acceleration, which is 0.299. So that means tension will equal to 560 times by 0.299, add 600. So the tension equals to 767 Newton. Right. Now, part C, explain how you use the assumption that the cable is light or inextensible. So just like what we explained before. Now, if the cable is light, that means the mass of the cable was not included in the total mass of the two objects. So we could write down that as the explanation. So the mass of the cable was not included in the total mass. So as you can see in part A, we only consider the mass of the car and trailer, but not the cable. Okay, for part II, what about inextensible? Well, that just means that the car and the trailer should have the same acceleration. So that's what it means for inextensible. So the car and the trailer have the same acceleration. Okay, good. Now let's move on to look at the second example. Okay, so now in this question here, before we do this example, let's consider what would happen in our previous example if the car started to brake. The braking force is acting on the car only, so there is nothing to slow down the trailer. The cable would go slack and the trailer would get closer to the car. This is why for touring, we use rigid objects such as a toolbar, which can exert thrust as well as tension. Let's have a look at the next example. Okay, so here in this question, the trailer is attached to a car by a light toolbar. The mass of the trailer is 350 kilograms and the mass of the car is 680 kilograms. The car starts to brake and decelerate at 4.6 meters per second square. Assuming all other resistant forces can be ignored, find the thrust in the toolbar. Let's have a look at the diagram. Okay, so this is the trailer and it's moving towards the right hand side. However, it has a deceleration of 4.6. That's why my A equals to negative 4.6. Now, because it's connected by a light toolbar, so the deceleration will be the same as the car is also A equals to negative 4.6. Now, on the toolbar, sorry, not on the toolbar, on the trailer, the only forces acting on the trailer would be the thrust. Now, be careful here. It's not like what we did in the previous example, the T goes towards the car. However, in this case, T is acting in the opposite direction. And on the diagram here for the car, there will be a braking force acting on the car, and the thrust would go towards the car. Now, if you forget about the difference between tension and thrust, please go back to our previous chapter and review the examples on tension and thrust. Okay, so now just a little quick note. Okay, so what is a thrust force? So a thrust force is directed towards the object. Okay, so that's something to help you understand the diagram a little bit better. Right, maybe I can write this down as well. So thrust force is directed towards the object. Okay, and tension is away from the object. That's the difference. Right. So what are we actually looking for? So we are looking for find the thrust. Okay, now let's consider all the forces acting in the car and the trailer. So what is going on the car? Well, on the car, we have two forces, the braking force and the thrust. Because the car is moving to the right-hand side, that means the thrust will have the positive sign and the braking force will be the negative. So let's use F equals ma, and we'll get T minus B equals M, which is 680 times by A, which is negative 4.6. And what is happening for the trailer? Again, we use F equals ma, and the only force acting on the trailer is the thrust, and it's going against the direction. So that will be negative T equals to 350 times by negative 4.6. Okay, now, so if you look at the two equations, okay, because the question is only asking for the thrust, so we don't need to worry about the braking force. And from the second equation, we can straight away work out the thrust. So T equals to 1,610 Newton. And that's it. So really, you don't even need this equation. Okay. However, in the exam, just be careful that sometimes they may be asking you to work out the braking force in the next part. Okay. Right. So that's all the examples we're looking at for connected particles. Now let's do some example. Let's do some exercise. So this is exercise 22D. Again, please draw the diagrams and labeling all the forces with the direction of motion and acceleration labeled on as well. And again, be careful in the question if it's talking about the tension or it's talking about the thrust. Remember what we said in the previous example, thrust is acting towards the object, but tension is acting away from the object. So here are the question 1 and 2. Question 3, 4, and 5. Question 6, 7, and 8. And here are the answers.